get into. So section 1-4 is going to talk about sample spaces and probability. This is going to be our introduction to probability. Probability is defined as the chance of an event occurring. Okay, you probably use probability in your everyday life, usually maybe a subjective form of it, or maybe a more scientific or empirical form of it. Whenever you read or hear about the weather report, there's a 20% chance of rain, right? What does that mean? Intuitively, you sort of have an idea that there's 20% odds of it raining and 80% odds of it not raining, right? If you can interpret the probability that way. Or maybe you take a test and you are just thinking to yourself, like, I feel like I failed that. And if somebody asks you to quantify how sure you are that you failed it, you might say, I'm 80% sure that I failed that test, right? In that statement, you're not saying that you got an 80 on the test. You're saying that there's two outcomes, either pass or fail the test, and you're very confident with 80% certainty that you failed the test, right? So these are different ways that we use probability in our everyday life, but fundamentally it is a measure of the chance of some event occurring. And so we need to talk about events in a particular context, okay? So some examples of how probability is used would be weather forecasting. Like I said, there's a 75% chance of snow. Well, if somebody told you here in Texas, there's a 75% chance of snow today, then you could probably think of all the factors that go into the weather in Texas and probably look them in the face and say that they're full of BS, because there's probably closer to 0% chance of snow today in Texas, where we are, okay? But probability is also used in setting insurance rates, right? Like you might have heard that your insurance rate for your vehicle is higher when you're younger, because after you turn, I don't know, 25 or 26, the insurance companies will charge you less on your vehicular insurance, your automobile insurance, because presumably most people, once they get a little bit older into adulthood, become safer drivers, right? Younger people tend to drive more recklessly, okay? So they have a lot of data backing up and supporting that idea. And so they set some probabilities that help them calculate how much they're going to charge you for their insurance, right? And that's fundamentally how a lot of insurance companies work. Insurance, whether it's life insurance, whether it's medical insurance, right? You could have multiple comorbidities for something like heart disease, metabolic disease, diabetes. Those things would, if you had those conditions, then it's likely that medical care would cost more money for you to receive that treatment, right? So your insurance rates for medical insurance might be more expensive as a result of those conditions that you have, okay? Now, there are some technical aspects of it in real life in practice where, you know, there have been some laws that have been passed to sort of protect people that have quote unquote pre-existing conditions. But nevertheless, having pre-existing conditions does mean or indicate that you are a riskier person to treat, right? And that fundamentally is related to probability. So we're going to get into some terminology here. A probability experiment is a chance process that leads to a well-defined result called an outcome, okay? The simplest kind of probability experiments we can talk about are like flipping a coin. That's a probability experiment because we know what the two outcomes are of one of those trials, okay? So a trial is one instance of the probability experiment. So an example, very simple example, is flipping a coin. That would be an example of a probability experiment. And we have some outcomes for a single trial of the probability experiment. So what are the two possible outcomes for flipping a coin?
Heads or tails?
Heads or tails? Now, realistically, if you were to flip a coin, there's a very, very tiny percent chance that the coin could, land on the table and then land on the edge, right, of the coin. But for our purposes and for simplicity's sake, we generally think of that being a 0 probability. And so there's only 2 real outcomes. Either the coin falls on head side up or tail side up. Okay, so those are the 2 outcomes of that probability experiment. Okay. A sample space is the set of all possible outcomes for that probability experiment. So if we just think about some simple experiments here, we talked about tossing one coin or flipping a coin. Then the sample space is just you listing off all of the possible outcomes that you can get from tossing one coin. So from a coin toss, you get either heads or tails. So I'm going to put heads, tails there. Those are the only 2 outcomes that we would get. Okay. If you were to roll a die, a 6-sided die for simplicity's sake, right? I think that we've all probably rolled a 6-sided die before. How many outcomes are there?
Six.
Yeah, you could roll a 1 or a 2, a 3, a 4, a 5, or a 6. But there are no other numbers on that die because it's a 6-sided die. So your outcomes are 1, 2, 3, 4, 5, and 6. Okay. What about answering a true or false question? What are your outcomes there? What is the sample space?
2.
Yeah, there's only 2 outcomes in that sample space, but the outcomes are either true or false. Okay. What about tossing 2 coins? What are your outcomes there? Any ideas?
Is it 4?
Yeah, it's 4. And you can enumerate what those outcomes are if you think about flipping 2 coins, right? So one way that you could think about this is using a sort of tree diagram, where if you flip one coin, so this is my first coin flip, then you get 2 outcomes there. You either get heads or you get tails. But then once you go from whatever the outcome is there, you're going to flip another coin. So this is going to be the second coin flip. So either you got a heads or a tails on that first coin flip, but either way, once we get the heads, you could get a heads on the second coin flip, or you could get tails on the second coin flip. Or if we got tails on the first coin flip, then we could get heads on the second coin flip, or tails on the second coin flip. And so that's one way that you can sort of enumerate what the sample space is here. If you look at the ends of these, this tree diagram that we have here, where we branched out for every instance or every trial of the experiment, we had 2 outcomes. So if we just read this tree backwards, our options are that we got heads and then heads. That takes care of the first branch. Or we got heads and then tails. That's the second branch. We could have gotten tails then heads. Or we could have gotten tails and tails. Okay, so there's 4 outcomes there. I'm going to abbreviate here as double heads, heads then tails. We could have gotten tails then heads, or we could have gotten tails and tails. So 4 outcomes. Does anybody have any questions about that? Okay. The next example is asking us to find the sample space for rolling 2 dice. And so if we roll 2 dice, and we're going to assume that these are 6-sided dice, then maybe we can think about first, how many possible outcomes are there if we roll 2 6-sided dice? Does anybody have any ideas there?
Is it 12?
It is not 12. And I see in the chat, Daniel is saying 36. And that's correct. There are 36 possible combinations or outcomes if we roll 2 dice. So you can see what we're doing there. Maybe you can start to see what we're doing there. When we had 2 coins that we were tossing, we had, let's say that I'm going to put a space here and a space here. For the first coin, how many outcomes were there? Well, there was only 2 outcomes for flipping a coin, right? Heads or tails, 2 outcomes. And then for the second coin flip, there was 2 outcomes. So if we multiply those together, we get the 4 outcomes total for that sample space for tossing 2 coins. So if we're rolling 2 6-sided die, then each of those has or possible rolls for those die individually are 1 through 6. So there's 6 possible outcomes there, and then 6 possible outcomes on the second die. So the total number of combinations that we can find there is just by multiplying those 2 numbers together. Okay, but how would we enumerate that that sample space so that we can list all of the possible outcomes? Well, one way that you can do it is by setting up a table, and this is the same thing as a multiplication table, essentially, or very similar to setting up a multiplication table. You could say that here we have die 1, and our options are 1, 2, 3, 4, 5, and 6. Maybe I should have given myself a little bit more room to work here, but we'll just go with it. And then die 2 is over here, and we have 1, 2, 3, 4, 5, and 6. So I'm just making myself a little grid. Okay. And then the outcomes of that experiment are essentially obtained by saying, okay, well, if we just cross these, we're not necessarily going to multiply these like a multiplication table, but we're going to say that it's possible to get a 1 here and a 1 here. So that's a 1 and a 1. Or we could get a 1 and a 2. Or a 1 and honestly, I should be doing this as 1 and 1. This should be 2 and 1, since I'm talking about die 1 first. Die 1 is 3, and then this is die 2. 4 and 1, 5 and 1, 6 and 1. Right? And so we can fill out the rest of this probability space, right? Or sample space. And this will be the total of all of the combinations that we can get. We can get 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6. We can get 2 and 2, 2 and 3, 2 and 4, 2 and 5, 2 and 6. 3 and 2. Okay. But I think that you guys see the pattern that's going on here, right? Are you guys all right with me not completing this table? Just because I think it would eat up a lot of time. And I think that you guys have the idea. Does anybody have any questions, comments, or how you would enumerate or list all of the possible outcomes here?
No.
Okay. So let's do an example just so we can make sure that we understand how to sort of enumerate the sample space. So let's say that we had an experiment, a probability experiment, where I flipped a coin and rolled your standard 6-sided die. How many possible outcomes are there? Any ideas? I'm seeing an answer in the chat. Is everybody okay with it being 12? Twelve is correct, right? Because if you think about the outcomes for the coin flip, there's 2 outcomes there. And if you think about the outcomes for the dice roll, for the die roll, there's 6. So if I multiply those together, I should get 12, right? And if you needed to list the entire sample space, you could get heads, and you could get 1, 2, 3, 4, 5, or 6 on those die, the roll of that die. Or you could get tails and one of those numbers from the die, right? So in total, you could get H1 or H2, H3, H4, H5, H6 if you wanted to sort of code it that way, just so you didn't have to write out heads every time. Or you could get tails in any one of those numbers, okay? So a lot of times in any discussion of probability, it always comes up that we're going to talk about another type of experiment involving an ordinary deck of cards. Okay. So if you were to take an ordinary deck of cards, let me go ahead and zoom in here. And you were asked to find the sample space for drawing one card from an ordinary deck of cards, then usually you would enumerate it this way, right? These are all of the cards in your standard deck of cards. There's 52, not including the jokers, right? If you're a poker player. You have what are called the suits, which are the numbers or Jack, Queen, King, or Ace. Wait, the suits are the hearts, diamonds, spades, and clovers, right? Or clubs. Is anybody here a poker player? Because obviously I'm revealing myself that I'm not a poker player. Okay. Pretty sure these are called the suits. And then I think the face cards refer to the ace, jack, queen, king. But in any case, you have the cards numbered from 2 through 10, and then you have a jack, queen, king, and an ace for each one of these suits. So there are 13 cards of each suit. So in total, 13 times 4 gives you that 52 total cards, right? Those cards are unique because they have some identifier, like the number or the face. And then they have the suit, which are hearts, diamonds, spades, and clubs. And then even still, you can sort of categorize them as the hearts and diamonds are red faces. And then your spades and clubs are black-faced cards. Right? Okay. But in total, there are, if you were to draw just a single card from the deck, then you could think of that as a probability experiment. What is the probability of finding one of these cards? Well, it's 1 out of the 52 total, right? Maybe intuitively you sort of understand that, even though we haven't started to compute probabilities yet, 1 out of 52 sounds reasonable. Okay. You could have another experiment, such as thinking about the gender or sex of a child that's born, right? So find the sample space for the gender of the children if a family has 3 children. Use B for boy and G for girl, and use a tree diagram to enumerate or find the sample space for the gender of that 3 children in a family. Okay. So the way you would do this is sort of think about child 1. What are the options? Again, here we're simplifying real life down to a gender binary. Male and female are going to be our only options. So we're just going to use boy and girl as our code. B versus G. Okay. So child 1 could either be a boy or a girl. But child 2 could also either be a boy or a girl, right? So we could have in this family, the first child come out a boy, and then we get a boy after that, or a girl after that. Or if we had in that family, the first child come out a girl, then you can have a boy or a girl after that for child 2. And then child 3 could either be a boy or a girl, a boy or a girl, a boy or a girl, a boy or a girl. Okay. And then if you wanted to enumerate or list all of the possible outcomes here, you just sort of walk backwards in the tree based on the tips of these branches. So it's possible that in a 3-child family, you could have this outcome, boy, 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 or you could have boy, boy, girl. So that takes care of these first 2 branches. You could have boy, girl, boy, or boy, girl, girl. And I'm starting to lose sense of what the meaning of the words boy and girl mean because I'm saying them so often. Then moving on, we could have girl, boy, boy, girl, boy, girl. That takes care of these branches here. And then finally, we could have girl, girl, boy, and girl, girl, girl. 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. And that should make sense because if we're sort of using this counting technique that I introduced, if you think about the outcomes for these children, I'm going to put little spaces here. For child 1, there were 2 outcomes. For the second child, there were 2 outcomes in the trial of that experiment. And then for the third outcome, there's 2 choices also in terms of gender or sex. And so there should be a total of 8 outcomes. When you multiply 2 times 2, you get 4, and then times another 2, we should get 8. And these are the outcomes specifically. So this is our sample space. Does anybody have any questions or comments? Cool beans. Okay. Got some more terminology for us. So an event consists of a set of outcomes of a probability. Of a probability experiment, rather. An event can be one outcome or more than one outcome. An event with one outcome is called a simple event, whereas an event that has two or more outcomes would be called a compound event. Okay, so some examples here. An event with one outcome would be like if a die is rolled and shows a 6, then the result is called the outcome, since it's the result of a single trial. Okay, so already sort of intuitively, we've thought about these experiments. Again, we're calling them experiments. If you roll a die, that is a probability experiment. Okay, and whatever the result is what we're calling the outcome of that single trial of that probability experiment. Okay. But in that example where I said, let's enumerate the sample space of this experiment wherein you flip a coin and roll a die, that's technically a compound event because we've done two things there. We can think about the probabilities or the outcomes of flipping the coin, and then think about the outcomes of rolling the die separately, and then sort of combine them into a compound event. Okay. So another example of this would be the event of getting an odd number when a die is rolled. That's called a compound event because it consists of 3 outcomes or 3 simple events. Okay. That's another way of thinking about it. We have just one experiment, but the outcome that we're interested in is the probability of, or the event of getting an odd number. Whereas if we look at the sample space for a die, 1, 2, 3, 4, 5, and 6, then we have 1, 2, 3 possible odd numbers. So there are 3 simple events that go into getting an odd number when you roll a die. Okay. Now, as I alluded to this at the beginning of class, there's 3 basic interpretations of probability: classical probability, and that's sort of what I was calling probability theory. That's the mathematical basis of probability. There's empirical probability, which is based on our experience and data that you collect in the real world. And then there's subjective probability, which is more or less like a wishy-washy guess of probability. Like, I don't know, you might go into work one day and say, I have a 15% probability of getting a raise today, right? Which is kind of low. I don't know, on a normal sort of work day, you don't just go in and assume that you're going to get a raise. Or maybe another example would be like, you walk out of a job interview and you're feeling good about that interview, and you might say subjectively to yourself, I feel really good. I'm like 95% sure I got the job. Okay. That is a numerical designation that you've given to the feeling that you have of whether or not you're going to get that job. And if you're feeling really good about it, that gut feeling is a subjective probability. Okay. But we're going to start this thing off by talking about classical probability and how we calculate and actually quantify those kinds of probabilities. These kinds of probabilities probably are based on these simple experiments that we've been talking about, like coin flips and rolling die. And it relies on us actually enumerating the sample space to come up with a numerical probability that the event will happen, and assumes that all the outcomes in that sample space are equally likely to occur. So when we think about what is the probability of a set of parents having a child that's a boy versus a girl, presumably there's a roughly equal chance of having a boy versus having a girl. Now, there might be some data out there that suggests that maybe there's a slight asymmetry in those probabilities, where maybe it's a little bit more likely to get a girl versus a boy or vice versa. I don't know. But for simple terms, we would think of that the gender of the child as being very much like a coin flip, right? As only having two possible outcomes that are equally likely to occur. Okay. So how do we calculate the probability then? Well, I think that this notation looks a little bit crazy, but if you'll just go with me here, this P of E, this is sort of like a function notation, which if you haven't seen algebra in a while, it might look a little bit crazy, but in any case, this is the probability that an event will occur. Okay. N of E is the number of that desired outcome basically happening in the sample space. So if you can count up how many times that outcome or that event occurs in the sample space, then that's the number that you're going to put as the numerator in this expression, the number of desired outcomes, over or divided by the number of total possible outcomes. So this notation is a little bit complicated. N of E is basically how many times an event occurs in the sample space. And N of S is equal to the total number of outcomes in the sample space. So as long as we can find those two numbers, we can calculate what the probability is in classical terms. And again, when we enumerate the sample space, or basically list out all the possible outcomes, we're sort of treating it as though all of those events in the sample space have an equally likely chance of occurring. Okay. You won't always get a nice, neat fraction here, and sometimes you want to convert those fractions to decimals. So we have a rounding rule for probabilities, and that probabilities should either be expressed as fully reduced fractions, or they should be expressed as decimal numbers that have been rounded to 2 or 3 decimal places. Okay. Sometimes you get extremely small decimal values. And so in those cases, it's going to be permissible to round the decimal place to the first non-zero digit after the decimal point. So if for whatever reason we got a probability that was equal to 0.000000532, it would be permissible to write that, since if we rounded this to just 2 or 3 decimal places, we wouldn't capture these significant digits over here. So we're just going to round that to 0.0000, let's see, 1, 2, 3, 4, 5, 1, 2, 3, 4. And then we'll round to the first non-zero digit. This 3 is not going to bump this up, so we're going to leave that as a 5, and then that will be our answer. But in all other cases, when we have 2 or 3 decimal places, we'll just round to 2 or 3 decimal places, depending on what the problem asks us to do. Okay. So now we're going to practice using classical probability to calculate some probabilities here. Let's find the probability of getting a red face card, a jack, king, or queen, when randomly drawing a card from an ordinary deck. Okay. So the event here that we're interested in is what? Well, we want a red card that is either a jack, queen, or king. Okay, so in this example, they're not considering the ace to be a face card. So we'll have to take that as it is. So how many possible, how many events do we have here of finding a red card that's a jack, queen, or king in a deck of cards? How many ways could we do that? Any ideas?
13 times 3, because we're not doing the aces one.
13 times 3. Oh, I see what you're saying. No, we don't really need to multiply anything here. We're just counting how many ways can you get a red face card, right? So if you think about the deck of cards, let me go ahead and bring this image back up, right? We call the hearts and diamonds red cards, right? So how many jacks, queens, or kings are there that are red?
6.
6. That's it. There are 6 of these cards that are red because the other jack, king, and queen cards are black cards. So for this particular example, how many ways can we get this one event, a red face card? There's just 6. Does that make sense? So if you already have the sample space enumerated like we do in this image here, you're just counting up these events. So the event of getting an ace or 2 of hearts or 3 of hearts and so on and so forth, right? We're just trying to count up how many ways can we get a red face card, and these are the ways, these 6 ways. Okay, so a red face card, how many ways can we do that? N of E is just equal to 6. There are 6 outcomes that correspond to those conditions, right? And then how many outcomes are there possible if we're drawing a card from a deck? So we're looking for N of S, right? What is the total number of outcomes in the sample space? If you're not considering the jokers, there should only be 52 outcomes in a deck of cards. Okay, so if that is simple enough to get, and again, some of you might not be as familiar with a deck of cards as others, that's perfectly fine. It's not a requirement here, but it is helpful. And then we have the number of times that that event occurs in the sample space and the number of possible outcomes in the sample space. So the probability of that event occurring is just equal to 6 over 52, which can be reduced to, what is this reduced to? Three over 26. Okay. But again, if you're not comfortable with fractions there, it's perfectly fine to go ahead and take your calculator out and then just take 6 divided by 52. And you get this probability. We're going to round this to 3 decimal places because it doesn't specify in this example what to do. So I'm going to say that this is approximately 0.115. So 0.115. Either of these would be fine. They should be the same value. I'm just going to double check that that's correct. 3 divided by 26, same number. Okay. I always want to check that I reduce that fraction correctly. So I was just checking to make sure that I did that division in my head. All right. Does anybody have any questions there? Finding the probability from a deck of cards.
No.
Okay. I have another example. What is the probability of drawing an ace from a standard deck of cards? Remember, the probability of the event is equal to the number of times that that event occurs in the sample space divided by the total number of outcomes in the sample space. Sorry, that's an S here. And so we should know that the denominator, the total number of outcomes in the sample space of drawing from a deck of cards, is just going to be 52 for our denominator, right? Because there are 52 possible outcomes. But how many ways can we get an ace when we draw a card from the deck? Might be a weird way to ask that question, but I assure you it's not a trick question. Let's see, in the chat, we have 4. Yeah, there are 4 aces in the deck. So it's possible to get an ace of hearts. Rather than spelling this, I'm going to put an ace of diamonds. We could get an ace of spades, which looks something like that ish. Or we could get an ace of clubs. Something like that. Looks more like a piece of broccoli, but okay. So there's 4 possible ways to do that. We could reduce that fraction if we wanted to I don't know, 2/26. But you probably just want to throw that into the calculator as 4 divided by 52, and then we'll round that off to 3 decimal places. So 0.077. So there's a 7.7% chance of, if you draw 1 card from the deck, of it being an ace. Okay. Does anybody have any questions or comments there? Okay. The next example. Gender of children, yet again. If a family has 3 children, find the probability that exactly 2 of the 3 children are girls. Okay. So here, the event that we're interested in is that 2 of the 3 children are girls. Okay. So we need to find out how many times that occurs in the sample space. And so what you might want to do is, I keep using the phrase enumerate the sample space, but I mean like literally list all of the possible outcomes that you can get there, right? So we said before, it's possible to have, these are the outcomes in our sample space. I'm going to put sample space as S. It's possible to have a boy, and a boy. Or a boy, and then a girl. And then we can sort of wobble that second position. So we could have a boy, a girl, and a boy, a girl, and a girl. Okay, so we wobbled that position there. So now we're going to wobble this position. It's a very technical term. So I'm going to change that to a girl, we'll go with a boy and a boy. We could go with girl, a boy, and then a girl. Then I'm going to wobble this middle position now. Girl, girl, boy, girl, girl, girl. Right, and those should be the 8 outcomes that we said that there should be, right? Because there's 3 children, so 2 times 2 times 2 should be 8. 1, 2, 3, 4, 5, 6, 7, 8. So if this is our entire sample space, how many ways or how many times in these combinations that we have here, do we have 2 out of the 3 children being girls? Well, let's go ahead and see what we have. So we have 2 girls here, boy, girl, girl. Girl, girl, boy. Sorry, girl, boy, girl has 2 girls in it. And girl, girl, boy also has 2 girls in it. And this says you have to be very careful with the wording that exactly 2 of the 3 children are girls. So even though this last option, this last outcome in the sample space has 2 girls in it, it has 3 girls total, and we're looking for the probability that exactly 2 of the children are girls. So that means that we only have these 3 outcomes here that meet those qualifications. Okay. So the number of ways that this event could occur in the sample space is 3. The total number of outcomes in the sample space is equal to what? Should be the 8 total outcomes that we have here. And so to find the probability of this event occurring, we're just going to take 3 and divide that by 8. 3 divided by 8 is 0.375 with no need to round that off because it's at 3 decimal places. Does anybody have any questions or comments there?
No.
Okay. So in some of these problems, you want to take a lot of care and caution when you're reading them, because in probability theory, it's important to understand the meanings of the word and the meaning of the word or. And means that those 2 events occur at the same time. Okay. And in logic and in mathematics, the word or has 2 meanings. There's an inclusive or, and there's an exclusive or. So if we say that 2 things happen and we're using inclusive or, then you're thinking either one or the other, or both. That's inclusive or. Exclusive or is either one of the events occurs or the other event, but not both. Okay. So you have to make sure that you understand which or is being used to determine or to count the correct number of outcomes for a particular event. Okay. And they should clearly indicate in the instructions what they're talking about there. So I'm going to jump into some more examples here. And we're going to try to figure out these probabilities and figure out whether we're using an inclusive or an exclusive or. Okay. More about drawing cards from a deck. A card is drawn from an ordinary deck. Find the probability of getting a king. So we're going to start off with our first option here, A. probability of drawing a king. So let's say that drawing a king is going to be our event E. So how many ways can we obtain that event when we draw a card from a deck? How many kings are there in the deck, in other words?
Four.
Yeah, there's 4. And then how many cards are there in the deck in total, or how many outcomes are there in the deck in total?
$52.
52, right? It's not changing. So we can say that the probability of obtaining a king, probability of obtaining this event, is equal to 4 divided by 52, which we can go to our calculator, 4 divided by 52, and we're getting approximately equal to 0.077. And I'm pretty sure that we had computed something very similar to that before. You'll find that whenever we're dealing with cards, that some of these events that you have similar probabilities or the same probabilities, depending on how many of those events, how many times you can count that event in the sample space, right? And so if you're really familiar with cards, then depending on what game of chance that you're playing, let's say at a casino, you could quote unquote count the cards to figure out what your odds are. And if you're really good at reading the odds or the probabilities, then chances are you know when to quote unquote hold them versus fold them. Okay. B. What's the probability of getting the 4 of spades? Well, if I translated this, the 4 of spades is like saying, what is the probability of obtaining a 4 and that 4 being a spade at the same time? Right, so that single card has these 2 qualities. So how many 4 of spades are there in the deck? Anybody know?
1.
Are there 4 of them? Well, we can always go back to our diagram of the cards here if you're not super familiar with it. Let me pull that back up. Here's our diagram of the cards. How many 4, can anybody locate where the 4 of spades is, right? The 4 of spades is this guy. Are there any other 4 of spades?
No, it's just the 1.
It's just the 1, right? So if you draw from a deck of cards, then the number of ways that you could obtain a 4 of spades is just that one way. And then if we enumerate the sample space, we know that there are 52 cards in total there. So the probability of getting this event of drawing a 4 of spades is just 1 out of the 52 possible options. So we'll just take 1 divided by 52. And we get 0.019. We can round that off to 3 decimal places and call it a day. Does anybody have any questions about that one? Okay, C. The event that we're talking about now is we want to see what the probability of obtaining a face card. Okay, now remember that a face card is going to be a jack, a queen, or a king, And here I'm going to say or is inclusive. So we want to count up all of the Jack, Queen, Kings, regardless of the suit and regardless of the color, right? So if we go back to our deck of cards here, in total, how many Jacks, Queens, and Kings are there in the entire deck? Yeah, there's 4 of each, right? 1, 2, 3, 4 Jacks, 1, 2, 3, 4 Queens, 1, 2, 3, 4 Kings. So this portion of the entire deck constitutes how many outcomes? Well, there's 12 outcomes, right? 4 times these 3 rows, or these 3 columns, rather. Okay. So the number of face cards defined here as Jack, Queen, or King, the number of that event is 12 because there's a Jack of Hearts, a Jack of diamonds, clubs, and spades. That's 4. Then there's a Queen of Hearts, diamonds, clubs, and spades. That's 4 more. And then a King of Hearts, diamonds, clubs, and spades. And that's 4 more. So that's a total of 12. The entire sample space is 52, right? That's how many outcomes, how many possible cards there are in the entire deck. So the probability of finding this event, of drawing a face card, is 12 over 52, which we'll go ahead and throw that in the calculator and find that probability. 12 divided by 52. 0.231, because we're going to round that to 3 decimal places. Does anybody have any questions there?
No.
Okay. There's a couple more examples within this example, but we're just going to move on. Okay. So these problems are similar to what you're going to see in your homework. So let's just talk about them and see if we can calculate their classical probabilities. So if a die is rolled 1 time, again, we're assuming that it's a 6-sided die. Find these probabilities, enter your answers as fractions or as decimals rounded to 3 decimal places. So they'll specify how many decimal places. What is the probability of rolling a die and getting an odd number? Well, first of all, I think it's helpful to write your sample space out so that you know what all your outcomes are. When you roll a die, you can get a 1, a 2, a 3, a 4, a 5, or a 6, assuming that this isn't what is it called, Dungeons and Dragons, and you're rolling like a 20-sided die, right? Okay, so for a simple 6-sided die, how many odd numbers are there?
3.
There are 3 odd numbers, right? 1 is odd, 3 is odd, 5 is odd. So if the event is the odd numbers, the number of ways that you can get that event there's 3 ways, right? How many total outcomes are there in the sample space?
Six.
Just 6. 6 total outcomes. So the probability of this event happening is going to be 3 over 6, which reduces to 1/2, or you could interpret that as 0.50. Okay. The second question is asking me, what's the probability of getting a number greater than or equal to 3? So I'm still rolling that die. My sample space. I'm going to stop writing sample space and start writing just S. 1, 2, 3, 4, 5, and 6. Which of these outcomes is a number that's greater than or equal to 3? Or how many of the outcomes are greater than or equal to 3?
4 of them.
4 of them, right? So if we take these 4 outcomes, those are the outcomes that are either equal to 3 or greater than 3. So that tells me that the probability of this event is going to be equal to 4 over the total number in the sample space, which is 6. And this should reduce to 2 over 3. If you throw that into your calculator, that's 2/3, 0.667. Does anybody have any questions about that one? I think this last one is fun. And that is, what's the probability of getting a number greater than 3 and that number being an even number? Okay. So we might want to enumerate the sample space there. You could get a 1, a 2, a 3, a 4, a 5, or a 6. And then before, we wanted to see just what is the probability of getting something that's greater than 3 or equal to 3. Okay, so you want to be very careful here. This example for part 3 is saying that that number has to be greater than 3. It's not saying that it can be equal to 3. So we need to highlight those numbers that are greater than 3 here. 4, 5, and 6 are greater than 3. And we want that to be an even number. Okay, so only the even numbers that are greater than 3, which are 4 and 6. So how many ways could this event occur? What is n of e?
Is that 2 over 6?
Yeah, so the number of ways that we can get a number that's greater than 3, that's an even number, is 2. So the probability of this event will be the 2 over 6, or 1/3, which is 0.333. Does anybody have any questions there? Okay, moving along. I think that's enough example problems there to get you going. We're going to talk about probability rules because there are some rules for probability. You've probably noticed that all of these numbers are decimal numbers that are less than 1. And so probability of any event occurring is a number between 0 and 1, and it includes 0 or 1. So for the first probability rule, all you need to know is that probability of any event occurring is some number. You can represent it as a fraction or a decimal, and that's going to be between 0 and 1. 0 and 1 are included. When we talk about probability, sometimes we talk about it in terms of percentages, but if we are close to the number 1, that means that we are certain, 100% certain, that that event will occur. Okay. Like if I asked you, if you flipped a coin, what is the probability of getting a heads or a tails? Right? That event is kind of silly to think about because I just asked you, what is the probability of getting either of the 2 outcomes? And those 2 outcomes seems to take up the entire sample space. So it's 100% certain that you will either get a heads or a tails. So it doesn't really make a whole lot of intuitive sense to talk about probability in those terms. But in any case, the closer we are to a 1, the closer we are to 100% certainty. Okay. If we say that something has a near 0 possibility, or probability rather, then we can think of that as something having a 0% chance of occurring. Okay. We usually talk about something having a 50-50 chance of occurring, like a flipping a coin. That'll be right in the middle. And what we mean is that that probability could go either way, that there's only two outcomes and one or the other outcome will occur. So you can think about this like flipping a coin. Okay. And this notation here is just saying that the probability that any event occurs is between 0 and 1, and it could be equal to 0 or it could be equal to 1. Okay. But in any case, probability will always be a number between 0 and 1. If you get a negative number, then you've calculated something wrong. If you get a number that's larger than 1, then you've calculated something wrong. That value for your probability should always be between 0 and 1 and should be positive. So you'll have some questions in the homework that will ask you, based on that information alone, a probability experiment is conducted. Which of these cannot be considered a probability of an outcome in that experiment? Okay. And right away, this first option is not a possible probability because you have a negative number, right? So we cannot have negative probabilities. Okay. What about B? Based on the simple rule that a probability has to be between 0 and 1, is it possible to have a probability of 0.61? Is 0.61 between 0 and 1? Yeah, that one works out. What about 2/3? Is it possible to have a probability of 2/3?
Yes.
Yeah, and so it might be helpful to calculate that as 2 divided by 3, and you'll get 0.667. And that's a number between 0 and 1, so that's possible also. We have a positive number between 0 and 1. Is it possible to have a probability of 23%? I'm coming up yes in the chat. Yeah, because 23% is equal to 0.23, which is a number between 0 and 1. Is it possible to have a probability of 105%? That's a no, because that's a 1.05. That number is outside of the allowable range here for probability, so that's no. Can I have a probability of 0?
Yes.
Yeah. So in that rule, we just said that probability needs to be between 0 and 1. 0 could be included, 1 could be included, but we can't go outside those boundaries. So we could have a probability of 0. Cannot have a probability that's negative. So the next one is not going to be a valid probability. It's possible to have a probability of 1. And is it possible to have a probability of 1.8?
Yes.
No,
Why?
because we said a probability has to be between 1 and 0. It cannot be outside of those boundaries. So no probabilities greater than 1. Okay, so I should be very clear there. If that's a little bit confusing, then it might be here, right? Like when I said a probability of 23%. 23% as an actual number is represented as 0.23, right? So we have to make sure that we're converting our percentages to decimals in order to assess whether or not those are valid probabilities. This is already written as a decimal number and it's greater than 1, right? So that tells us that that cannot be a probability. So that first probability rule is very simple and very strict. Your probabilities need to be a positive number between 0 and 1. 0 and 1 are included. We cannot be below 0, which would be a negative number. We cannot be above 1. Okay. Another probability rule that we have is that the sum of all of the probabilities in a sample space is equal to 1. Okay. So this is sort of like what I was talking about with the, what is the probability of flipping a coin and obtaining, if I could spell today, obtaining either a heads or tails. Okay, if you think about the sample space S, there's only 2 outcomes for flipping a coin, heads or tails. That's the entire sample space. So if I'm asking you what is the probability of obtaining heads or tails, then how many ways can I get either a heads or tails? Or how many times does a heads or a tails occur in the sample space? Well, the heads only occurs once. The tails only occurs once. But combined, that's 2, right? 2 of the outcomes in the sample space are embodied by this outcome of obtaining a heads or obtaining a tails. So this would be 2 on top of my probability. And then what is the total number of outcomes in the sample space? Well, the sample space only has 2 outcomes. So 2 divided by 2 is equal to 1. And so that's what we mean when we say that the sum of the probabilities of all of the outcomes in the sample space should equal 1. That's because the probability of obtaining a heads is equal to 0.5. The probability of obtaining a tails is 0.5. And if you add those 2 probabilities together, which are the entire sample space in this case, that's 0.5 plus 0.5, which is equal to 1, which is what we got here. Another example of that is listed here. If you think about the probability of obtaining one of the outcomes of a dice roll, right? You roll a 6-sided die. Okay. Then each of the probabilities for getting one of those outcomes, either a 1 through a 6, is going to be 1 over 6, since there's just one of these outcomes for each of these numbers. So 1 over 6 plus 1 over 6 plus 1 over 6. If I add all of these probabilities together, I get 6 over 6, which is equal to 1. Okay. Probability rule 3 is that if an event cannot occur, that is, if its event contains no members in the sample space, then it has a probability of 0. So for instance, if I asked you, when a single die is rolled, find the probability of getting a 9. Well, this outcome of getting a 9 when you roll a dice does not occur. So you can think of that as 0/6, since there are 6 total outcomes in a dice roll. And since the number of times or number of ways that you can obtain a 9 when you roll a die is 0, that's going to be 0/6, which is just 0. So again, it seems a little bit simple and nonsensical, because that's like me asking, if you were to flip a coin, what's the probability of you getting red? Well, that's not one of the outcomes in a coin flip, right? So the number of ways that getting a red when you flip a coin is 0 out of the 2 ways that you can, the 2 outcomes in the sample space. So 0 divided by 2 is still 0, right? So if that event cannot occur, then it has a probability of 0. Okay. Probability rule 4 is that if the event is certain, then it has a probability of 1. So if you were to be asked the question, when a single die is rolled, what is the probability of getting a number less than 7? Well, all of the options, right, for the face-up value when you roll that die are numbers that are less than 7. 1, 2, 3, 4, 5, and 6. They're all less than 7. So it is going to be 100% certain that if you roll that dice, that you will get a number less than 7, right? So again, it may seem absurdly simple, but if the event is certain, then the probability is 1. Okay. There's some more terminology here. The complement of an event is denoted by E with this line above it. Okay. And this is the set of outcomes in the sample space that are not included in the particular event E. What does that mean? Well, I think that finding some complements will help us understand what this means. So if you think about the event of rolling a die and getting a 4, then I'm going to sort of enumerate or illustrate what the complement of this event is. Okay. So if we roll a die, we can get 1, a 2, a 3, a 4, a 5, and a 6. E is getting that 4. So I'm going to go ahead and denote this with orange and say that there is the event that we're interested in this example. The complement of this event, E with a bar above it, and I'll denote this in blue, that event contains everything except for the original event. So the complement of getting a 4 is the event of getting a 1, a 2, or a 3, or a 5, and a 6. So 1, 2, 3, 4. Sorry, not 4, 5, 6. So you can think of it as, if you've enumerated the sample space and you've seen what all the outcomes are, if we're talking about the event its complement is everything other than that event. Okay. So if you were to think about the probability experiment of selecting a letter of the alphabet and getting a vowel, what are the vowels? Well, I feel like English is a little bit weird. A, E, I, O, U. And then we're not going to consider Y because Y is a sometimes vowel for some reason. But then what is the opposite of the vowels? Does anybody happen to remember this? This is like a throwback to maybe grammar school.
Wouldn't it be all the other letters?
It would be all the other letters. We call the other letters
Consonant?
the consonants. And there are too many of them for me to list them all out, right? But it would be all of the other letters, your B, C, D, blah, blah, blah. The consonants are the complement of your vowels. Okay. So if I said, what's the probability of obtaining a vowel if you were to randomly draw letters from the alphabet? Well, there's 1, 2, 3, 4, 5 vowels out of how many letters total? 26 in the English alphabet?
Yes, there's 26.
Yeah. So that would be the probability of getting a vowel when you randomly choose a letter out of the alphabet would be 5/26. When you can reduce that or represent it as a decimal if you wanted to. Okay. So another example would be selecting a month and getting a month that begins with J. So there you might want to write out, well, what are all of the months? So we have January, February, March, April, May, June, July, August, September, October, November, December. Okay. The ones that start with a J, January, June, July, and that's it. Okay, so the complement, we have E is represented by this event here. Then the complement E bar is going to be the set of outcomes that are not in E. In other words, it's all the other months that don't start with a J. And I'm just going to draw arrows here to say that the outcome of getting a February, March, April, May, or an August, September, October, November, December, those are going to be outcomes that we're going to say are in the complement of this event. Okay. So rather than going into another example here, if you have an event, its complement can be thought of as whatever is not the event. Okay. And now we have a rule for events and their complements in probability. Okay. So this Venn diagram is supposed to indicate an event versus the sample space that event occurs in. So if you can think about this graphically, if we have an event in a sample space, usually the sample space is written as a big rectangle. And so if we're just focusing on this diagram here on the left of a simple probability of some event, then you can think of this portion here as being the event itself. Okay. And whatever proportion of the area this circle takes up in this rectangle, the whole rectangle is the sample space. The circle here is the event. And sort of the ratio, or if you were to divide the area of the circle divided by the total sample space, you would get the probability of that event. Okay. The complement, though, the complement is everything outside of that circle, outside of that event. So, and that's sort of what we've been dealing with in those examples, trying to illustrate what that is. So the complement here is everything outside of that circle. The complement of the event, which is denoted by E with a bar over it. But the rule for complementary events is that if you were to add an event and its complement, you get 1, the entire sample space. And you can sort of manipulate this algebraically to get these other complement rules, that the probability of a complement is just 1 minus the probability of the event. And that's typically what we'll see here. This is the most typical version of this rule. So let's take a look at our first example, right? In a study, it was found that 23% of the people surveyed said that vanilla was their favorite flavor of ice cream. If a person is selected at random, find the probability that a person's favorite flavor of ice cream is not vanilla. Okay, so if we know that the event that we're talking about, sorry, I put a bar above that when I shouldn't have. The event that we're talking about here is that vanilla is the favorite flavor. Then the complement of that is that the favorite flavor is something other than vanilla. Okay. And what they want us to find here is the probability that a person's favorite flavor is not vanilla. So we want to find this probability, which is the complement. Okay. What is this 23% they've given us? Well, they said 23% of the people surveyed said that vanilla was their favorite flavor. So that means that they've given us P of E, the probability of that event, is equal to 0.23. So if you want to find the probability that a person's favorite flavor is not vanilla, then we can use this rule for complementary events and say that the probability that somebody does not like vanilla when they're randomly selected is 1 minus the probability that they do like vanilla. So 1 minus the probability that they do like vanilla is 0.23. And so we'll find that probability here. 1 minus 0.23 is 0.77. So using the complement rule, we can find the probability that someone does not like vanilla. Does anybody have any questions there? Okay. Well, we don't have that much time left, and we still have to talk about empirical probability. So we'll leave that for Wednesday. And so we're not done with section 4-1. We'll pick that up on Wednesday next class. And so that homework assignment, I have changed those due dates for this week's homework to Friday. Okay. So you might be able to get in there and do some of your homework, but some of it might be confusing until we've completed this section. So it's available to you guys if you want to jump in and work on some stuff ahead of time, but we'll just go ahead and finish this up next class, right? If you have any questions, you're more than welcome to hang back, but otherwise, enjoy the rest of your day.
Have a good one.